Hello and welcome to the second video of Universal Relative Theory. My name is Ricardo Porta. I'm going to be explaining for you now how I explain the movement of galaxies, so the galactical movement in our universe, with the same theory that you saw in the first video. And that is the Universal Relative Theory. And attraction and repulsion, yeah? If you didn't see the first video, go there, because I'm not going to explain everything again, because there is no point to do two videos, right? So, how galaxies, what kind of galaxies do we have? We have actually three main groups of galaxies. I would say that we have elliptical, we have lenticular, and we have spiral. Why that order? Because I believe that's the order of creation. And with this kind of gravity, you're going to discover many things. That things they make sense in other way. So many scientists, they think the same of me. Other scientists, they think not. The spiral is the second galaxy, because a good lenticular galaxy is the third. But not. Elliptical galaxy is the first one. Does everybody agree? Why? Because this is when a star starts to attract another star that attracts another that attracts another. Actually, there is attraction and repulsion there. So stars, they are repelling and attracting themselves. And that, actually, there is no movement. But when you have a big star in the center, that big star will start to influence all the stars around it. So then you're gonna have a disk, but just like our solar system. So but it doesn't work so like our solar system, but it's maybe slowing down as far the stars they are. But there's one thing, just stars, they have a much bigger power, and what's happening in a galaxy is really strong. So what's happening is that there are stars that a big star is attracting stars, small stars, that is attracting other stars that even has bigger power, or they are but they should be in another position there, but they cannot go forward because the other stars are in front of that. So it influences gravity in one way that you have a brutal gravity there. So it can be that you have lenticular galaxies that actually the speed is bigger than a simple solar system. But actually the rule works in the same way, because you have a central star. What can happen with a lenticular galaxy is if that star that's in the center dies. Yeah, normally it's the oldest one, so of all those stars. So in the stellar age, if you saw my first video, that star was one of the first to be created, and it was attracting, shocking with other stars and become bigger, and so that became really big star. So or was a gas planet that was so big, and that became a gigantic star, and it has a very big power of attraction, what bring all the stars together to it. And many stars, they can repel. Some stars they could not, but the other stars that are in front are repelling that and repelling that one as well. So then you see that there is lots of gravity there. And if that star dies, so let's give an example. We have a lenticular, yeah, in a representation here, and we have here the center star. So you have a big star in the center. That star has a circle, is a green circle, that is the curve in space and time. All right, that's the attraction. That's the limit of attraction. Each point, you could say that's 50 million stars. Yeah, it's a yellow point, and the red one as well. The thing is that that stars, the yellow stars, they are being attracted by that star. Yeah, it doesn't mean that the one that's closer to that star has more power or less power. No, it was just the order of attraction. So they are also competing between them. There is stars pressing stars inside of that galaxy. They would like to go further or to move for another place that would be more comfortable for them or more logical for them. But they cannot, because that other stars, they are already there and occupying that space. So, but doesn't matter. That star just died. Why that died? Maybe it doesn't support anymore the repulsive force. Like you see, in the green line, you have the curve in space and time, but you can see that you have red stars outside, red groups of stars. That red group of stars, they are being attracted by the ones, the yellow stars that are in the edge, not by the big stars, the big star in the center. The big star in the center just attract the yellow ones. And the ones that are in the edge attract the red ones. So that red ones could be attracting other stars, that could be attracting other stars, and the repulsive force became so big that that star that was in the center lost its power, and then the repulsive force will just touch in the center of that star. What happens that the star will expand itself, will lose all properties of attraction and repulsion. What happens with that will be a dead matter. But the thing is that once that star die, you are going to have almost that. That star die, and this is the weakest point, not just in that galaxy, but outside of the galaxy also, because there is gravity outside, but there is no gravity in that point. There is a missing gravity. What's going to happen? That galaxy that was being pressed together because that star in the center will relax. So stars are going to be pushing stars, and the poor stars that are in the center, that they were closer to that big star, they are going to be the first ones to suffer that new galaxy transformation. So the mass of that galaxy will be expelled for that repulsive force to quasars, for north and south. It's never gonna escape for another place because it's everything fulfilled with gravity. The only place that it has to go is north and south, so would be quasars. But the next stars that are going to be there as well are also going to shock because they have not the same power of that big star to keep the other stars that are relaxing far away. So what's going to happen is that those stars are going to collide and keep feeding the quasar until the stars that are in the center, the new stars that are coming, they are going to be able to stop. So they are going to repel themselves and be able to keep all the galaxy together. And so they keep the rotation, and they formed a new rotative nucleus or rotative core. So what's going to happen is that core will be actually replaced by a core of many stars, and this is what you have in the spiral galaxies. So it's a lenticular galaxy that became a spiral galaxy. Can happen in another way. A spiral galaxy that becomes a lenticular galaxy. Yes, if a big star would be close to the center and it would take the place of the other star, then it could happen. But the good thing is that there is no black hole. There's just a core made by many stars. Yeah? What's going to happen that after when you have that core will keep the attraction and repulsion. So all the stars in that lenticular galaxy that we saw are going to be that are repelling and attracting between them. So the stars, the star that is in one point is attracting all the stars that are close to that and repelling that as well. So and so that connection between some stars, they are going to create the arms. So all the stars are going to follow the movement of that rotative core, but in different points. So they are going to be connected with different stars, depending of its position in the galaxy. So then you're going to have what I called before a wagon movement, so a train movement. So the locomotive is the core, and the last wagon would be the extremities of the galaxy that are going to have the same speed or close to that, because they are not connected physically, but with repulsion and attraction, and it can have some oscillation. But the right velocity, the right speed, would be the same speed as the core. If there is no oscillation, no alteration, they are going to speed as the core. And in the end, you're going to have a formation of a spiral galaxy, like we see Andromeda and other galaxies. So this is why you have, but I saw one galaxy that was, the arms, they were far away from the nucleus, and they had just a arm of light, and then, they are different galaxies. So if you have a core or a star in the center that has a much more repulsive force, so it has a big repulsive force, or it has it will repel all the stars that would be in arms from far away, but the arms, they are going to keep connected, but they are going to have that drawing. There you have tons of galaxies because each core is different than the other. They are not the same. Black hole. I love black hole because it's the biggest fantasy ever. What is in the center of the galaxies? They asked 100 years ago or 200 years ago because they didn't know. What happens is that if you look at a galaxy like ours, and knowing the size of our galaxy, if you have something that make all those stars together, you would need an enormous star, like you see in lenticular galaxies. In lenticular galaxies, you see an enormous star in the center. But in our galaxy, we don't see that. And sometimes you have a galaxy like Andromeda that is gigantic, and a very little galaxy with a big star in the center. But Andromeda doesn't have that. And then you'll be thinking, wow, but Andromeda should have a star that's much bigger than that. So what is bringing everything together? What happens is that we create black holes because that everything that's black and dark is everything that we create to say we cannot see it because it's black. We cannot see it because it's dark. So black hole was never proven until today. It's just a mathematical calculation. So what is a black hole? A black hole is this. Yeah, you have something that they say that's very dense. There is a big density, and that density sinks space-time. It doesn't curve. Now, our sun curves space-time, but that star is so dense that it sinks space-time and sucks even light, because there is a big gravity, and that gravity would be inside of, in the center of all the galaxies. So then you can explain the movement of the galaxy a little bit, but not so much, because a black hole would not make the galaxy in the center of the black hole would be much faster. It's just like when you were taking a shower taking a bath, and you take the tap of the bath, you're gonna see that the hole is much more powerful than the rest of the bath. It's not the same thing, and with time, all the water is going to be sucked. And this doesn't happen with our solar system, with our galaxies. So actually, black hole doesn't exist. You know what proof I have? I have this one. Do you remember Apollo 15, Galileo test? You had a feather and a hammer. Astronaut took that two ones in the moon, in the atmosphere of the moon, and he just left the both down. They fell down in the same speed, and they touched the floor in exactly the same time. What happens is that space doesn't matter how heavy you are, because weight you don't have there. Doesn't matter how dense is a star, it will curve space and time with its mass. Why they created that black hole? Because they could not explain gravity. And until today, nobody can explain gravity because they don't see the work of Albert Einstein. If they would open the eyes for what Albert Einstein was saying when he died, they would come up in an observation like I am. And I'm sorry, but I believe that I am right, but I'm not laughing about anybody. Contrary, I'm very sad. So if you have a bowling ball, or if you have a soccer ball in a space, they are going to have the same curve in space and time. Okay, mass curves space and time, just that. If you have a little thing, it's gonna have a very tiny space-time curve. Yeah, that's exactly that. It's not if you are heavier. Oh, but why some stars they are alone? Because repulsive force is much stronger than attraction. Why? Because why some stars they have a so powerful? Because attraction is much stronger than repulsion. There is so many answers, so many ways to explain that with repulsion and attraction, and it works perfectly. In my opinion, yes. Nobody could prove until now for me that I'm wrong. So thank you very much. This is everything. I'm going to keep going, working with that, and of course, I'm going to just remember Albert Einstein in this end, and of course I would like to dedicate to him, because he did everything. Even what I did now, I don't believe that I did. I wouldn't be nothing. I would be just a guy. But I'm very happy that I did this video. And I'm going to say a phrase that for sure I don't know. I never heard him saying that, but I'm sure that Albert Einstein said, "I don't like to brush my hair." I'm sure. I'm sure that he said that. He must have said that. I have no idea why he had this hair. It's not nice. But a great man. And thank you very much. Your work was very good. And he's right. It's just that. I'm sure it's just that. Even I'm going to keep going with Lagrangian points. Let's see what I'm discovering with that. Because I believe that the biggest tip that God led to us was the Lagrangian points. And we just discovered that. It's just amazing. God would never do a black hole. Like a black hole doesn't exist. It's just mathematical. You know, you can make anything using mathematics. If you want to make that curve in space and time gigantic and so deep as the universe, you can do. But it doesn't mean that it exists. There is no black hole. Just go have a look in a video that you have on YouTube about Apollo 15, the feather and the hammer. And you're going to see that density in the universe has nothing to do with curve in space and time. Okay? Thank you very much. I wish a very nice life, and well, soon I'm going to do more videos. Just search for the newest version. Yeah? You're going to see that. Okay, thank you. Bye.